Although that clip may have seemed real, those graphics were made possible using the power of ray tracing. Ray tracing is a way to simulate the behavior of light in a 3D space using mathematics and physics. Watch. Ray tracing can transform simple gaming scenes like this into beautiful lifelike environments by simulating how light actually behaves. Ray tracing can also be used in movies and TV shows as well. The foundations behind ray tracing were developed by artist Albert Dürer in the 16th century. He used strings and weights to sketch 3D perspectives onto a 2D plane, which eventually led to the modern graphical ray tracing. Later on, these ideas were applied by Arthur Appel, who used the same logic to create 3D images onto a 2D screen, which was finally revolutionized by Turner Whitted, who developed recursive ray tracing. Non-recursive ray tracing works like this, where a light source is determined to be hitting an object and therefore we add light there. However, this is unnatural and unrealistic. Instead, we opt to use recursive ray tracing, which allows for reflections and refractions. It allows for light to bounce around as it does in real life, which allows it to look more realistic. Now, let's get into the math, like how we determine intersection points, light gradients, and the randomness of light bounces.
Rays are the basic idea behind ray tracing. A camera sends them into a scene. We begin with the camera at one point in space. It emits many rays, but to understand the process, we isolate one. Its equation is P of t equals E plus TD. E is the start, and D is the direction. The parameter t tells us how far along the ray we are. Changing d rotates the ray, so the ray keeps the same form but points in a new direction. In 3 dimensions, x of t, y of t, and z of t work together to describe that same motion through space. Step 2. Ray-sphere intersection. We begin with the ray starting at E and moving in direction d. That gives the parametric equation. Next, we place a sphere in the center C and radius r. A hit happens when some point on the ray is exactly 1 radius away from the sphere's center. So we write the condition, the distance from P at t to C squared equals r squared. Now we substitute the ray equation into that condition and collect terms. That turns the geometry into a quadratic. That discriminant tells us the kind of intersection we have. Delta less than 0 means no hit. Delta equals 0 means a tangent. And delta greater than 0 means 2 hits. In 3D, the picture gains depth, but the logic stays the same.
Step 3. Surface normals. On a sphere, the surface normal is a vector pointing straight outwards from the surface. As the point moves, so does the direction. To compare the directions, we should use the dot product. The formula is a dot b equals the magnitude of a times the magnitude of b times cos theta, where theta is the angle between the two vectors. As theta decreases, cos theta increases, translating to more light. Step 4 is lighting and shading. Diffuse lighting acts as a base, where n is the normal vector and L points to the light. A smaller theta gives a larger n dot L. At 90 degrees, n dot L equals 0 since cos theta equals 0, so diffuse lighting just vanishes. For unit vectors, this becomes n dot L equals cos theta. So diffuse intensity is proportional to the max between 0 and n dot L, which just gets rid of negative values. For specular light, R is a reflection vector and V is a view vector. The highlight is strongest when V aligns with R, or when theta is smallest, measured by R dot V. So specular intensity is proportional to the max between 0 and R dot V, but not to the power of S, where S is the shininess variable, which adjusts the sharpness or dullness of the highlight.
Step 5 is global illumination with Monte Carlo sampling. Light can reach a surface directly, or bounce off another surface first. In a real scene, there are far too many bounce paths to compute exactly, so we sample a few random directions instead. Mathematically, we estimate the indirect light by averaging the samples, add the sampled values, then divide by the number of samples. Few samples look noisy. More samples make the estimate smoother, more stable, and way more realistic.
In its most basic form, ray tracing is a process of solving many math equations per second to simulate the behavior of light, and it's revolutionized the graphics of the digital world. But now, let's get back to our game.